Good morning again. In the previous lecture, we have started with discussion of comparators, and today we will continue on that. So let's refresh our memories from the previous lecture. A comparator is in fact, some sort of a digital device at the same time. It's an op-amp, but what you do is you compare two inputs and provide one bit digital output. So people use these comparators in, for example, A to D converters or D to A converters very frequently. So these are very important components for digital or mixed signal design as well. So in the ideal case, of course, what you need to do is when you compare two inputs, when P input is larger than N, for example, you want to get high output. When P is less than N, you want to get low output. And in that case, you have zero offset, infinite gain for the ideal case, of course, and the trip voltage is 0 volts. So when you have a change at the output. But in reality, this will never happen, unfortunately. First of all, you will have finite slope. The amplifier, even if you have like 10 to the power 4, 10 to the power 5 gain, it's not infinite. So there will be some slope. But the good news is this slope is very high for most of the time. So this change happens less than in 1 millivolt. So that's one good thing. But if you are seeking for high resolution for A to T converters, for example, you want to make this change in much less than 1 millivolt. You want to make this gain as high as possible. The other thing is this tripping will not happen exactly at 0 because of physical properties of the transistors and the op-amp. This is going to shift either right or left, so you will observe some offset voltage. So in reality, the change happens at some positive or negative voltage depending on the op-amp non-idealities, which is the offset voltage. So in this case, your trip voltage will be this new offset voltage, assuming that the gain is very large, of course. And we are talking about digital signal, and the output high voltage may not be exactly equal to VDD, or the output low voltage may not be exactly equal to minus VSS. But this is not a big deal because in reality, what you do is once you create this transfer function, you can add some latch in here to maximize. So, I mean, these latches, in fact, like two consecutive CMOS inverters. And for CMOS inverters, you know that output high is VDD, output low is minus VSS. So by putting these two components, you can pull this thing to VDD, and you can pull this thing to VSS without any problem. So this third non-ideality is not a big deal. The other thing is distortion or limited linear range. So in this case, you have infinite gain and you don't have any distortion. In this case, again, the gain is not infinite, but the characteristic is linear. But again, this is not a very critical thing because when you add this latch in here, these two CMOS inverters next to each other, you can make the gain very high and you can minimize the effect of this distorted operation. Because keep in mind that you want to use this thing as a digital component. You want to get 1 bit output, either 0 or 1. And therefore, you will never operate your comparator in this range. You want to minimize this range so that you can increase the resolution. And in that sense, when you add some extra gain stages in here, like latch, this linear range is not a big deal. This thing is not a big deal. The most important or critical thing is, of course, offset voltage. The others you can solve somehow. Anyway, one critical thing for the operation is the propagation delay. Of course, you want your comparator to be as fast as possible, but there are components like internal capacitance or compensation capacitance putting some extra delays in the operation, and these delays will define the overall speed of your system. Think about an A to D converter, for example. You are using many comparators. You want your A to D converter to operate very fast. You remember from 3 to 12, for example. And in that sense, this comparison should happen at very, very high speed. And this propagation delay in here is the limitation. So you want to keep this thing as as short as possible. And as I said, internal capacitances, compensation capacitances, so on and so forth, limits the operation speed of your comparator. There are some tricks in here. Maybe we can mention about them later on. For example, you need to use a compensation capacitor because you want to ensure that your overall system is stable for all the time. But during the comparison cycle, if you can use a clocked operation, for example, during the comparison cycle, you can disconnect that compensation capacitor to increase the speed, for example. These are some tricks that you can use, and we can mention them later on. The other critical thing is sensitivity. It tells you what is the minimum input voltage difference that you can resolve. Because if you operate your system in this range, you may get inconsistent results or meaningless results because you are looking for either logic 1 or logic 0. So this range is not desired. What you can do is, as I said in the previous case, you can put some extra gain stages like latches or CMOS inverters to minimize this inconsistent or gray range. Of course, the sensitivity level defines the gain required for proper operation, and we have shown that in the previous lecture. So when we talk about the trip voltage, we talk about two different cases. We start with the simplest case. So this is in fact a comparator, and this comparator is in fact has one input. So you are comparing your input with some voltage which is not shown in here. In the differential case, it is very easy because we know that when we apply the input, we are comparing it with some constant voltage and provide the output. But in this case, as you see, we have only one input and one output. And what is the comparative voltage? It's not shown in here. The trip voltage is in fact that voltage. So when you draw the transfer characteristic, output and input, you see such a characteristic. So it looks quite similar to the previous cases, previous characteristics. So what you do is, when your input is lower than this voltage, assuming that the gain is very high and that gray part is negligible, when your input is less than this voltage, in this range, you get logic 1. When your input is larger than this voltage, you get logic 0 at the output. So this is the comparating voltage, and that we call as trip voltage. Okay, and please keep in mind that the gain in here in this range is very large. So of course, you may worry about where should I take trip voltage, this voltage, this voltage, or this voltage. But if your gain is very large, the difference between this part and this part is negligible in the range of less than 1 millivolt or whatever. So that's why we take trip voltage as this voltage. For the differential comparator, the story is a bit more easier because you know what you're comparing with. But if you draw input as Vp minus Vn and output is like this one, so you can take the trip voltage as 0 volts, where Vp is equal to Vn. Okay. So input voltage in here defined as Vp minus Vn. And you can find output high voltage, output low voltage, depending on the transistor state changing. And but remember that you want to get the output always in here or in here. You want to operate this thing like a digital circuit. So your transistors will most probably will not be in saturation all the time. There may be some deviations, and that's of course reasonable. So comparators are somewhere in between analog domain and digital domain. So you have to consider their operation like that. And when you are talking about comparison, one significant problem is noise. your input is not stable, it may not be stable, there may be some external noises coming from the environment, or there may be some internal noises coming from the circuit. So that's a problem. And we have discussed this thing in the previous lecture. Let's say that you have an input like this one, like a sinusoid. At the output, you want to get a pure digital signal representing your input. So this is the input, this is the output. You have 1 in here, 0, 1 in, and 0 in here. But due to noise, because of the noise, in this transition points, at these transition points, your input may change, or your trip voltage, comparative voltage may change. This may result in inconsistencies at the output. Instead of having a pure square wave like this, you may have some glitches like this one, which is not desirable. And for that purpose, to eliminate this, you are using hysteresis comparator. Hysteresis comparator changes the trip voltage or the comparison voltage once you pass it. Like this one, we have seen in 312, and in 312, in fact, we are seeing an exaggerated version. The distance between these two trip voltages are significant in the range of volts. But in the actual application, this may not be that high. You may not need that high changes in the trip voltage. A small change may be good enough, considering that the noise values are low. I mean, if you have low noise circuit, the trip voltage change that you need maybe in the range of millivolts, maybe like 10 millivolt, maybe at most like 100 millivolt should be sufficient. So you don't need to worry about this exaggerated version of it. And what we have seen in the previous lecture was an hysteresis comparator made up of CMOS. So this is a typical hysteresis comparator. And when you take a look at the characteristic, as you may remember, it was something like this. It was not as exaggerated as like a typical Schmidt trigger. The distance in here is high enough to satisfy that you have noise immune operation, because noise levels are low. So when you take a look at the distance in here, it is not in the range of volts. It's going to be in the range of millivolts, maybe less than that, or maybe like a couple of, which is good enough, as I said, because you want to make your system noise immune. Anyway, so when you take a look at this circuit, it's an op-amp, of course, and we have solved this thing in the previous lecture, and we follow a different approach for solving. And what we have done is we take this whole thing as a load, and we try to find the load resistance, which is much more easier than other type of calculations. When you find the load resistance, you can put it in here, and then you can solve the circuit quite easily. And in fact, the gain that you find will be the slope either in here or in here. They will be the same. And we have done this previously. We define our load like this one, and we define input voltage Vx and the input current. You have to be careful about the directions. It is very critical. Then the rest is just writing a basic KCL and KVL. And you come up with two expressions for Ix, and you define your Vx. By doing simple math, you end up with this resistance, load resistance. And the rest is very straightforward for finding the gain. So we form this circuit, and then we find the gain. And the advantage is, by this feedback circuit, M5 and M6, you introduce this component. If you do not have that feedback, the overall gain will be minus GM1 divided by GM3, which is a low gain, which is not desired at all. But when you have this feedback, depending on GM6, I mean, if you can make this GM6 quite close to GM3, you can achieve a very large gain. And the good thing is, Because of this feedback, the turn on voltage for each transistor will be different than each other. Even though you have a perfect symmetry, the turn on voltages for M2 and M1 at the extreme conditions will not be the same, and because of that, you will observe different trip voltages. In this case, the trip voltage is defined as the point at which M1 and M1 or M2 turns on or off. Okay, it's defined as the boundary when M1 and M2 change state. And as I said, like the difference in these two voltages are not that high. You don't need very high voltages because all you want to do is you want to make a noise immune system. Okay, so when we take a look at the non-idealities, I told you that some of them are important, some of them are not that important. So let's remember them. Distortion may not be important because you are not going to operate your system in this part. As long as your gain is high enough, as long as your input is larger than the sensitivity voltage, minimum sensitivity level, that's okay, no problem. This VDD and VSSV output low may not be critical because you can add extra gain stages in here, like CMOS inverters. And we know that for CMOS inverters, output high and output low is exactly equal to VDD or minus VSS. So this is not a big deal. The other thing is finite gain, or you want to have very large gain. It's somehow related with your sensitivity. Worst come to worst, you can add extra gain stages made up of CMOS inverters to make this gain very high. That's also okay. So you can increase the gain. The cost is the comparator size increases, so forth. Of course, I mean, if you are working on an A to D converter in the range of like 20-bit, 22-bit resolution, that might not be this much easy, but for typical values, that's doable, no problem. The main problem is this offset voltage because it is unavoidable and it's going to change your the overall performance of the comparator. It's very critical. And the other thing is, this offset voltage sometimes may not be predictable. It may change depending on fabrication errors or misalignments or whatever. It's not that much controllable. So eliminating this offset voltage is a bit tricky. So people come up with some smart techniques to deal with these offsets. And in this lecture, we will see them. And it's known as AutoZeroing. What they do is they use clocked operation. This means that we have to put extra clock signal. This may look like a disadvantage, but on the other hand, you want to use these comparators in mixed signal design most of the time, like A to Ds or D to As. There is already a clock signal, so you can utilize it. So clocking may not be a big problem. So this is a typical structure for auto-zeroing. The clock signals are not shown in here. You use non-overlapping clock with phi1 and phi2. So I'm gonna put this phi1, phi2 components in here. And when you draw phi1 and phi2, they should be non-overlapping. They are non-overlapping. So when phi1 is high, let's take a look at the circuit structure. When phi1 is high, you should treat these transistors as perfect switches. And you may remember it from 311. In fact, a transistor is not a perfect switch all the time. NMOS transistor conducts low voltage very well with no voltage loss. PMOS transistors conduct high voltage very well with no loss. So if you need a perfect switch, you may need to use a transmission gate rather than a single transistor. So for perfect switching, you may need to use a transmission gate like this, one PMOS and one NMOS connected together. So this is transmission gate. So this is a designing strategy. If you have enough space, if you can create the inverted version of the inputs, using a transmission gate is not a big deal. But if creating the inverted version of the clocks is a problem, or if spacing or size is critical in the application, you may need to sacrifice from one of these transistors depending on the application. And in fact, still, this is a simplified design because when you try to implement this thing, these switches are a bit complicated than this one. You need to use clock fit reconciliation circuits in here. You need to use, other PMOS transistor here to minimize the voltage drop and so on and so forth. It's a bit more complicated than it is, but this simplified schematic may explain at least to explain how AutoZeroing operates. So when phi1 is high, this thing is short. This thing is open. This thing is short. This thing is open. So input is not connected to the system. Input does not affect anything. And this is the modeling of the offset voltage. So offset of the op-amp. So when phi1 is active and phi2 is not active, input is not connected, and the overall system looks like this one. This is AutoZeroing capacitor. You have to choose the value properly. It shouldn't be very high because it's going to occupy too much space and it's going to reduce the speed, overall operation speed, but you don't want to make it very small. Otherwise, you might not restore enough voltage on top of it. So that's a design parameter. And this is ideal op-amp. So what happens in here for an ideal op-amp? These two voltages should be the same. And the input current of the op-amp should be 0. In that case, what you do is you are charging up this AutoZeroing capacitor with the offset voltage with this polarity. So the upper part is positive. Please keep it in mind. So this is positive, and this point is positive. Okay. So eventually, after a while, after some, few nanoseconds or whatever, the voltage across the AutoZeroing capacitor becomes offset voltage. So this phi1 is for CAZ charging. And when you finalize this phi1 stage, voltage across the capacitor will be the exact offset voltage of the op-amp. And please keep in mind that the offset voltage is out of your control. You cannot tell an exact value before your design, before the fabrication, because it depends on the mismatches in fabrication. It depends on fabrication non-realities, and you don't have any control. It can be any value. The good thing in here, whatever it is, you copy that voltage on your AutoZeroing capacitor. In the second cycle, let's take a look at the second cycle. And while doing that, let me copy this part. And this one was phi 1, phi 2, phi 1, phi 2, phi 1. In the second cycle, when phi 2 is high, of course, phi 1 is low. In that case, this is short, this is open, this is short, this is open, and this is open. So what happens is, you have your input, now it is connected to the system. Remember that the positive polarity of AutoZeroing capacitors was on the left. So with that notation, you have copied voltage like this. And you may ask that there's some leakage in the capacitor. Capacitor is not ideal. So what's going to happen then? The answer is you have to do clocking very fast. You shouldn't allow discharge on the capacitor. In fact, these phi 1 and phi 2 are at high frequency, at high enough frequency to eliminate the effects of such leakages on the capacitor. So in that case, these two voltages are going to cancel. This not behave like you have 0 volts in here. So if this is a comparator, you are comparing your input with 0 volts, and you are not affected with the offset voltage at all. Offset voltage is not affected in that case. Any question?
Hocam benim bir sorum vardı.
Sure.
İlk cycle'da ki devreyi ben tam anlamadım. Hani kapasitans nasıl toprağa bağlandı? Toprak bağlantısı göremedim hocam.
Because here phi 1 is high, this node is grounded. Negative side of the AutoZeroing capacitor is grounded. Okay, so when phi 1 is active, the system is like this, where CAZ polarity is, the positive part is on the right. You are copying the offset voltage. For the second cycle, you have the input voltage, offset voltage, and now the polarity is reversed. And V out. So VOS effect is eliminated. Well, this is a very smart idea, and it looks very promising. But on the other hand, there are some problems. One thing is, of course, clocking operation. The system becomes complicated. This may not be a big problem because, as I said, like you're going to use it in digital component in any way if you want to make an A to D converter. So you can live with it. That's not a big problem. The other problem is switch design. There will be some non-idealities coming from the switches. So like, voltage drops. And to solve it, use transmission gates, which means that the system will be further complicated. Or charge injection, resulting in switching noise. And the solution is use more complicated structures or switches. So let me explain it very briefly. What is this charge injection? I'm not going to go into the detail, but maybe later on we can discuss it more. So what happens is this, in fact. When you have a switch, like this, this is your input, this is your output. If you have 0 volts, you want to have 0 volts in here. If you have 5 volts, you want to have 5 volts in here. But during the transition, when you change your input from 0 to 5 volts, or vice versa, the output should follow it, right? However, you have some physical capacitors in here, like CGS capacitor or CGD capacitor. So they keep some charge on top of them. So they require some discharging period. They're not gonna behave like, ideal open loop structures. And because of that, if you have any charge obtained on this thing at one cycle, that's going to affect the output directly. So when you take a look at input output, for example, you will observe that during the transition, it's going to result in some delays or some voltage changes at the output. So these are problematic. They keep charge at steady state. And they inject discharge to the output during the next cycle. I mean, this is a very rough discussion. I'm not, as I said, going into the very details on this thing, but you can keep it like in mind like this. There are some parasitic capacitances or some internal physical capacitances. They keep some charge, and that charge does not disappear. It's going to affect the next cycle. So to eliminate this, there are some circuit techniques. So what people do is when they use this main transistor, they put some extra transistors next to them. So this is main. And these two are to eliminate charge injection. But what they do is they use them as short-circuited. And if this thing is like W over L, this will be like W over 2L, W over 2L, half-sized. And the advantages if you have some capacitance in here, there will be some capacitance in here as well. And if this voltage is VDD, for example, well, I have to be careful about it. I think as far as I remember, it should be 0 volts, but whatever. So what they do is they create opposite amount of charge in here and in here, and they try to adjust the overall size of the capacitors to be the same, to keep the same charge amount. And they use them in short circuit because they want to change anything between input and output. They shouldn't be active in the operation. So what happens is if there is some discharging in here, for example, these two capacitors discharge opposite, the similar amount of charge with opposite polarity, and they cancel each other. The same thing happens in here. If this thing is injecting some charge, the opposite, the same amount of charge with opposite polarity is stored in these two capacitors, and they inject the same, and they are going to cancel each other. So the voltage in here or voltage in here does not get affected. You are not responsible from this thing because the discussion is more complicated than this. I'm just trying to give some hints on that. But what I'm trying to say is, if you want to implement such a circuit, these switches are not as simple as shown in here. You have to use more complicated structures. You may end up with like 6 transistor switch in here. One for NMOS transmitting low to low very well. One for PMOS transmitting high to high very well. And 2 transistors for injection compensation in here. 2 more transistors in here for injection compensation here. And of course, you have to use proper clocking for each transistor in here. So the circuit becomes much more complicated than this. And especially if you are doing very high resolution A to D comparator, for example, you have to do such complicated designs to have better performance. So a comparator is not a comparator itself. There are more extra components that you need to use with it, depending on the application and depending on the resolution which is required. So let's go back to discussion on auto-zeroing. So this is one approach, but of course, this is not the only approach. You can end up with many different architectures. And I'm going to show you another alternative. So like this one. So in this structure, for example, what you can do is you can have phi 1 in here, phi 1, phi 2, phi 1, and phi 2. So when phi 1 is active, let's show it with green, phi 1 active. This is going to be short, open, short, open, and short. So the equivalent circuit will be this is grounded. Let's put a sign like this on the left as positive. Like this one. So which means that if you have some offset voltage in here, you store the same voltage on the auto-zeroing capacitor. So when phi 2 is active, when phi2 is high, this is off, this is conducting, this is off, this is conducting, and this is off. And the equivalent circuit will be remember that this is the positive side. So if you have an offset voltage like this, they're going to cancel each other, and you compare your input with the output. The same thing. And another example,
Burada bir
which
şey
is on the right. Sure.
Bir sonraki ve bir offsetler hani kapasitörde ters oldu ya onun sebebini tam anlayamadım.
So let's take a look at in here. I define this left part as positive, right? So when I draw the simplified circuit, the positive sign will be in here. And I put the offset voltage as positive sign. I model the offset voltage as positive sign is closer to the op-amp. This can be negative. I mean, the offset voltage can be negative or positive. You will never know it. But you have to be consistent about your the polarity. So when you model it, I model it as the positive side close to the op-amp. So in this connection, this node should be equal to this node. So you have transferred the offset voltage in this polarity, right? So let's take a look at the second part. I mean, this part is positive. In this presentation, this part is positive. It's consistent. So in the new direction, I keep in mind that this is positive. It's close to the input. So look at it. It's close to the input and it's positive. And for the offset voltage, I modeled it as, like the positive side is close to the op-amp. I keep the same thing in here. Clear?
Anladım hocam. Teşekkürler.
Now let's take a look at the other structure, this one. So let's say phi1 is here, phi2 is here, phi1 is here. So when phi1 is active, you will have such a structure. This node will be grounded. You have the AutoZeroing capacitor. Let's put the positive side in here. You can choose any side as you wish, but you have to be consistent. That's the thing. You have to be consistent on the next cycle as well. So this node will be shorted. And what happens is, if you have an offset voltage at this node, it's transferred to the AutoZeroing capacitor. And when phi2 is active, let's do the same thing in here. I'm dealing with this circuit. Phi1, phi2, phi1. So when phi2 is active, this is open, this is open, this is short, and the circuit will look like this. I use this part as positive, as you may remember. You have the input, you will have the offset in here, you will have the offset in here. They're going to cancel each other. And your operation should ideally be offset independent. Any question in here? Any question up to this part? Okay, so we can stop in here. I'm stopping the recording.